In this unit, we're going to be looking at a different kind of motion. In the previous units, we looked at motion that we would call translational or linear motion. That's when things move from place to place. In this unit, we're going to be looking at a type of motion which is rotational. It's when things spin. There are so many parallels between the two that it's not like you're really learning a whole lot that's really brand new. But there are some differences. One of the differences is that the quantities that we use and measure for rotation are slightly different than the ones we used when we were doing translation. The three things we're going to talk about today are displacement, velocity or speed, and acceleration. Now, when we were doing linear quantities, a displacement, we'd use a symbol like an x, and we would use the units of meters to measure that. Our speeds or velocities, we'd use the symbol v, and the units would be meters per second. For acceleration, we use the symbol a, and the unit would be meters per second squared. Well, there is a slight difference when we talk about things that rotate. When something rotates, let's say we'll call this the position that, let's say this is a wheel. The position that the wheel starts in, it may rotate around to a different position. And where it's gone is an angle instead of a distance. And so when we talk about angular displacement as opposed to linear displacement, we would use an angle. The unit we're going to be using for angles is radians. And most of the time I will abbreviate that with just an RAD. We don't use degrees because radians works much better in formulas than degrees do. But we will learn how to convert the two. Now for speeds or velocities, the symbol that we use, by the way, I'm sorry, this symbol here is called theta, if you didn't already know that from your math classes, and it's typically used to represent angles. The symbol we use for velocity or speed is the Greek letter omega, and it kind of looks like a W, but it's a little bit more rounded, and it's not a W, it's an omega. The unit for that is radians per second. If you notice, there's a parallel here. Speed was meters per second, angular speed is radians per second. And the way we calculate an angular speed, the definition of an angular speed or velocity, is very similar to the definition for a linear speed or velocity, which is that the angular speed is the change in displacement over time. You can see that it's basically the same thing we did before, except for now we're using different symbols. And our acceleration, we use the Greek letter alpha, and its units are radians. And if you can figure out the pattern already, that's radians per second squared. And this acceleration is defined as the change in the angular speed per time, just like the linear version. We're going to see that every formula that we've learned so far this year has a rotational or angular equivalent. Once you get a handle on the symbols, you basically already know all the formulas. Now, one of the things that you're going to have to do when working with these is be able to convert from degrees to radians. So if I have an angle in degrees, let's say for instance 60 degrees, I need to be able to convert it to radians. And it's just a straightforward conversion like any other we would do. Now, I know a full circle is 360 degrees. And I also know from my math classes that a full circle in radians is 2 pi. So I can use that conversion. I could say 360 degrees equals 2 pi radians. Now in the end, the 2 over 360 kind of cancels, and you wind up with pi over 180, but it doesn't matter. You just do the math now, and you would wind up with something in this case like 1/3 pi radians. Now, this is science, this is physics. I'm not going to express these angles in fractions of pi like I did in my math class. I would actually put this in my calculator, and I would come up with 1.05 radians. We really need these in decimal form to use the formulas that we are going to be using. Now, one of the things that's important is being able to relate the linear quantities to the angular quantities. Back in your math class, you learned that the arc length, this distance along the outside of the circle, is equal to, now in math you use an S, I don't get that, we like to use x's for linear quantities in our class. That distance along there would be the angle of the arc times the radius of that circle. This is a really important relationship because you are going to have to be able to go back and forth between linear quantities and angular quantities many times. Now, there's also other relationships like this for speed and acceleration. A linear speed is equal to the angular speed times the radius. A linear acceleration is equal to the angular acceleration times the radius. So you see there's a pattern here. If you just take the angular quantity in radians or radians per second or radians per second squared and multiply it by the radius, you suddenly have your linear counterparts. You can use any of the formulas that we did for basic motion that we learned at the beginning of the year and solve the same types of problems that we did before. Again, our speed is going to be equal to our change in position or displacement per time. Angular acceleration is going to be our change in speed per time. This one especially is going to be used quite a bit because if we do some algebra here, we're going to wind up with the angular acceleration times time equals the change in angular speed, which is the final speed minus the initial speed. From here we can use this formula to do any number of basic type of problems.